So this chapter is on gravity. We will start with looking at Newton's law of universal gravitation, which is F is equal to G times M1 M2 divided by R squared. This tells us about the force that is generated, the force of gravity between 2 points. So if we have M1 and M2, then there's a mutual attraction, which is along the line joining these two objects, and it is equal to G times the product of M1 and M2 divided by R squared, where R is the distance. This is also called inverse square law because it is inversely related to the square of the distance. Now we can apply it to the earth. For a person standing on earth, the weight of the person is actually due to the gravitational attraction of the earth. And so when we talk about the distance, then that distance is from the center of the earth, the distance of the person from the center of the earth. And that is basically the radius of the earth. So if you look at this, the force with which the earth pulls an object, pulls a person, is actually the weight of the person. The weight is the force with which the person is being pulled by the earth. Weight is equal to mg, but that is also equal to the force applied by the earth if we write it using Newton's formula. G times the mass of earth times the mass of person divided by the radius of earth squared. If we compare these two, then m is common on both sides, the little m. If we remove that, then we find that G is equal to Gme, the mass of earth over radius of earth squared. So this is an interesting calculation. One could do this calculation by putting in the values. By the way, the capital G is called universal gravitational constant, and it is different from the small g. The small g is 9.81. The capital G is 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. Since this number is so small, that is the reason that normally we don't see gravitational attraction between everyday objects. Only if at least one of the objects is really, really massive, such as a moon or a planet or a star, only then the gravitation becomes, the force of attraction becomes significant. So if you go ahead, look up the mass of Earth, the radius of Earth, and put those numbers in the correct SI units, which is meters, then you'll find that this will come out to be equal to the 9.8 meters per second squared. There are other calculations and other questions that you might come across, which may require you to calculate the force of gravitational attraction or the acceleration due to gravity on other planets. And this same formula will work there. For example, if you want to calculate the gravity on the surface of Pluto, then you would do G, mass of Pluto, divided by the radius of Pluto squared. So that is something interesting to think about and to remember. Okay. The gravity does decrease as we go to higher altitudes. So suppose we are at some different height, which when measured from the center of Earth is 3 times the radius of Earth. Then to calculate the gravity over there, which we call G prime, you would do G me over 3 times the radius of Earth squared. So you can plug in the numbers and find the gravity over there. However, just because of the ratios and the way this formula works, we can also simplify this, and we can, without actually putting in the numbers, we can determine the gravity at this point will be 1/9 that of the gravity at the ground level. And so it will be about a tiny bit more than about 1.1 meters per second squared. So again, this is inverse square law. So if you double the distance between the objects, then the force becomes 1/4. If you triple the distance, then it's 1/9. If it's 4 times the distance, then it's 1/16, and so on. Then let's talk about orbital motion. So suppose this is the Earth, and we're talking about a satellite going in orbit around the Earth. In this case, the gravitational pull of the Earth is providing the centripetal force. So in order to do a calculation, we will do this. We'll write an expression for the force acting on the satellite. The mass of the satellite is m, and the distance of the satellite from the center of the Earth is r. So this will be the force of attraction, the force being experienced by the satellite. And this is equal to the centripetal force. This is a standard method in circular motion. Whenever something is going in a circular path, then this is one of the things to try, is always to figure out the expression for the force and equate it equal to mv square over r. So that's what we do here. We equate these, and then we cancel out the things that are common on both sides. So the little m and little m is common, and one of the r's can be canceled. And that leaves us with v is equal to square root of g m e over r. So this is it. This is the expression for the We can put an O here for orbital velocity. This is the orbital velocity. So when a satellite goes around the Earth in a circular path, then if we know the height at which it is going, the distance from the center of Earth, then you will be able to calculate the orbital velocity. And it's the orbital velocity of that orbit. It's not like a satellite can go faster or slower depending on how fast we want it to go. In that orbit, it's that fixed velocity that it can only go at that rate. Okay. Any object in that orbit will travel at this orbital velocity. For example, the International Space Station, we can do a calculation for the International Space Station of how fast it goes. And the speed with which it goes. You can do this calculation, but you'll find out that the speed at which it goes, it is able to complete one orbit around the Earth in about 90 minutes. Okay. So this is the formula for the orbital velocity. There's an additional calculation we can do, and which is that VO is the orbital velocity, so it is the distance over time. So within the distance, within the time period t, it travels a distance of 2 pi r. So we can put 2 pi r here. Distance over time is equal to square root of gme over r. We can do like this, and then square both sides. And then rearrange it some more. Bring the t squared over here and everything else to the left side. And we'll get 4 pi squared r cubed divided by gme is equal to t squared. So this is an interesting relation, a relation between the time period and the radius of the orbit. So you'll notice here that many of the things on the left-hand side, they are basically some kinds of constants. The only variables are the time period and the radius. So we can also write this as the time squared is proportional to the cube of the radius. Now, this is like Kepler's third law, which says that the square of the time period is proportional to cube of the orbital radius. So we can, in terms of calculations that have to do with orbiting around the Earth, we can use this formula and plug in numbers, and we'll be able to calculate the time period. For example, this is the one where you can calculate the time period of International Space Station going around the Earth. And when you will find this, you will find a number which will be in seconds. And then you can convert it into minutes, and you'll find that it is about 90 minutes or 1.5 hours. By the way, this orbital velocity for International Space Station is 7.7 kilometers per second. In doing these calculations, always remember sometimes in the question, you may be told the height above the surface of the earth. If you are told the height above surface of the earth, then to that you have to add the radius of earth in order to get the actual distance from the center of the earth, which is what goes in these equations. Another important topic to learn here is gravitational energy. So when we are on the surface of the earth or close to it, we say that the gravitational potential energy, which is denoted by U sometimes, is mgh. But when we start looking at the scale of the solar system, or we are going quite a bit of distance from the earth, then the expression for gravitational energy becomes minus gmem over r. So this becomes the expression for gravitational potential energy. This must be quite new to you and seem a little bit strange in having it as negative, but there is this principle in physics that anything that is not free to move, anything that is tied down or trapped in some kind of system has a negative potential energy. And so, because anything circling around the Earth would be trapped in the Earth's gravity, then it would have negative potential energy. So that's an important thing to know about. So this is the formula for gravitational potential energy. From this concept, if we draw a graph, it will look like this. So it's very negative. The closer you are to the center of the Earth, the more is the magnitude, more is the negative magnitude. But as you go further and further away, the gravitational potential energy becomes less and less negative and closer to zero, and it only becomes zero at infinity. So you can imagine that when some object is at infinite distance, at that point, it cannot feel the gravity. It is not uh, it is not captured by the gravity. So its negative potential energy will be zero. So there are some questions that you have to do in this chapter, which have to do with conservation of energy and how far will a rocket go. So it's basically conservation of energy, Ke plus Pe, something that you must have done before. Ke1 plus Pe1 is equal to Ke2 plus Pe2. So we will do it that way, except that in this case, the potential energy will be negative. The expression for the potential energy that you will write will be negative gmem over r. Right? So we write the expression for the kinetic energy. We say that the rocket starts here. It has some initial kinetic energy, half mv squared, and it has a potential energy minus gmem over the radius of Earth. And how high can it go? If you know the initial velocity, how high can it go? So at the peak, its kinetic energy will be zero. So we'll put that as zero here. And then what is the potential energy at this point? It will be negative G M E M over R E plus H, the new the new distance from the center of Earth. So this is how we construct the equation. And then usually we will want to find out the height. And so you can plug in the other numbers and then find the height accordingly. Then there is a topic which is called escape speed. Whenever we send these rockets, we shoot something with a very high speed. It goes quite far away, but eventually it gets pulled back and comes back down to Earth. But it is possible to shoot something with such a speed that it never comes back. That kind of speed is called escape speed. So how do we calculate the escape speed? It actually arises from the same equation. So one way to think about it is that you want to shoot something at such a speed that it can go all the way to infinity. Not coming back means that you send it all the way to infinity. So the height, we can replace it with infinity. If that becomes infinity, then this whole term becomes zero, right? Because of division by infinity, this becomes zero. And so then half mv square minus gmem over re is equal to zero, or this is equal to this, right? The m and the m cancels. This 2 can be cross multiplied over here. Simplifying this. And then we can take a square root on both sides. We can take a square root of on both sides, and looks like this. And this square goes away. So the escape speed or the escape velocity is given by this expression. It is interesting to note the similarity between the expression for orbital velocity and the escape velocity. The orbital velocity is square root of gme over r, and the escape velocity is square root of 2 gme over re. And this is the escape from the surface of the escape velocity from the surface of Earth. It is about 11.2 kilometers per second. We haven't found a way to shoot something with such a speed that it can just escape the orbit of the Earth. However, when we think about the kinetic theory of gases, small molecules, due to their collisions and temperature, sometimes can achieve these escape speeds, and they can escape the radius of the Earth, the gravity of the Earth, such as hydrogen molecules and other hydrogen molecules, helium atoms. They can achieve these speeds and escape the gravity of the Earth. That's why Earth's atmosphere doesn't have hydrogen. and helium in it. However, bigger planets like Jupiter and Saturn, they have a stronger gravity, and so they have a higher escape velocity. A higher velocity is needed to escape their gravity, and they are able to retain their hydrogen and helium. So the fact that some planets or moons have atmosphere and others don't has to do with their gravity. The more the bigger mass of the planet or the moon or the asteroid allows it to have an atmosphere, whereas a smaller size doesn't give it enough gravity to hold on to gases. All right, so and that is it for this chapter. I would like to add one more thing. In some calculations, your uh, potential energy could be provided to you as a graph. When you are applying this conservation of energy, then you have to calculate the potential energy, and sometimes that potential energy, sometimes also represented by capital U, instead of giving you a number for the potential energy or an expression, it can be given as a graph. So then what you will do is, if you know the distance, let's say it's I don't know, 100 meters, so you find that on the graph and then interpolate it and find where this how much potential energy is at that point. So here the potential energy could be 500 joules. So you will read it off the graph like that, and then put it into that equation. One more thing, uh, this will come in a future chapter in more detail, but I just want to give this to you ahead of time in case you may need to use it somewhere. Um, there is a relation between potential energy and force, and that relation is F is equal to minus du by dx. All right, so remember that, and if you and use it if you need to. Okay.